So a complex fraction is sort of like a fraction that is inside of a fraction. Okay, so here's what a complex fraction looks like. You take this fraction, we'll do like 5k over 36m. You take a second fraction, something like 15k over 9, and you divide those two fractions, making a fraction inside a fraction, or a fracception. It's a fraction that is made up of fractions. It's actually, it looks kind of horrifying, but you have done problems very similar to this when we talked last week about how to multiply and divide. What you have to remember about these complex fractions is that a fraction line, especially this big one in the middle, means divide. So what I'm actually saying to do is to take this fraction and divide it by this other fraction. So it's written like this, but I could also rewrite this as 5k over 36m divided by 15k over 9. How do I divide by a fraction? I flip and multiply. So this is 5k over 36m times the reciprocal 9 over 15k. So multiplying fractions is pretty simple. You just multiply straight across. 5k times 9 is 45k. And on the bottom, 36m times 15k, that's going to be pretty big because I'm going to have to do 36 multiplied by 15, which is going to be some giant number, mk. So 36 times 15, I'm going to come over and do that on the side here. 36 times 15. I will very quickly multiply this because none of you punks will get out a calculator and help your poor math teacher from having to do. It's too late, I already did it. So now the question is, can I reduce this? And the answer is, yeah, I for sure can reduce it by canceling these k's. K over k is 1, so those can go away. The real question is, can 45 over 540 be reduced? And the answer is yes. I don't know by what, though, but I do know that 45 and 540 can both be divided by 5. This ends in a 5 and this ends in a 0, so they can both be divided by 5. Yeah, 45 will go into 540, but if you didn't see that right off the bat, you could slowly get there by saying, okay, let's divide them both by 5. And then when you got done with that, the thing you would be left with could be divided by 9. But you have seen that both can be divided by 45, so on the top, 45 divided by 45 is 1. On the bottom, what is 540 divided by 45, smarty pants? 12m. And there's my answer. Now, I think the hardest part of this problem was reducing the fraction. So let's go back to that. Let's actually go back to this piece right here. Before we multiplied them, but after we had taken the reciprocal of the second one. And I want to show you something that's going to save you a lot of pain and heartache later, which is that you can reduce fractions before you multiply them. And there's several things that can reduce here. For example, 9 over 15 can reduce. Those can both be divided by 3, right?
Oh, okay.
So 9 divided by 3 and 15 divided by 3. And then look, the k, I can cancel those k's. And I can cancel these 5s.
Thank you.
And now it's really easy because on the top I just have 3, and on the bottom I have 36m, which is 1/12. So if you try to do a little bit of canceling before you start doing all this junk, you can sometimes save yourself a little bit of pain and suffering.
So why don't you show us that first?
What do you mean?
Or instead of doing Typing everything.
I like you to have as many tools in your tool belt as possible.
Okay.
I'm going to show you multiple ways to do it, and you are going to be grateful instead of whining and complaining. You're going to say, thank you for unlocking the mysteries of the universe for me, Mr. Taylor. You're my favorite teacher. So essentially, these are division problems that have just been written in sort of a weird way, but we're going to treat them just like they're division problems. Let's rewrite this as 8 over x, or 8x over x minus 4 divided by 3 over x plus 4. Okay, so then we'll flip the second one, the reciprocal of the second fraction, and multiply. There's actually not anything that can cancel right here before I multiply them. So on the top, I will have 8x multiplied by x plus 4. And on the bottom, I will have 3 multiplied by x minus 4. There isn't actually anything that I can cancel, and there's not anything that I can factor. So, I'm done. Can't cancel, can't factor. That's the end. That doesn't seem bad at all.
Oh, great.
However, if all complex fractions was a different way to write division, this would be kind of a waste of our time because we spent a great deal of time on division a while back. So let me show you one that isn't just as simple as treat it like a division problem. So this one is a very complicated, complex fraction. This is not simply a matter of flip the second one and multiply.
You have to eat the top one and the bottom and then go from there?
Yeah, the reason this one's weird is because now instead of a fraction divided by a fraction, I have two fractions added together divided by two fractions added together. I can get this looking like the old problems if I add these together. Like if I do x over y squared plus 1 over y and get a single fraction, then I can treat it like the other ones. So this goes back to what we did just a few minutes ago. How do I add rational functions? Well, if my denominators are y squared and y, what's the lowest common denominator of y squared and y? Why do you hurt me? Y squared. So I need another y on the bottom here so that these are both y squared. But if I multiply by y on the bottom, I got to multiply by y on the top. So what this gives me on the top is x plus 1y, or x plus y, over, they now have the same denominator, y squared. I need to do the same thing on the bottom. What will the common denominator on the bottom be? X squared. So I need to multiply this by x and multiply this by x. Now they have the same denominator of x squared. So when I add them together, y plus 1x. And now it still looks disgusting, but certainly looks less disgusting. So let's go ahead and clean this up a little bit. We're going to write this out like our long division problems. So numerator divided by denominator. How do you divide rational functions? You multiply by the reciprocal of the second. Times, and we'll go ahead and flip the second one. It's fine if you multiply and then reduce, but I do want you to try to reduce them first. You can save yourself a little bit of work. Do you see anything that will cancel before I multiply them together? Yeah, what about this x plus y here? And this is an x plus y here. Those can cancel. So what am I left with? There we go. So one of the methods to simplify complex fractions is to multiply by the reciprocal of the denominator, just like we did when we learned how to divide them originally. If you're not able to do that right off the bat, combine the numerator, combine the denominator, so you have one fraction on top and one fraction on bottom, then flip the second and multiply. That is one method you can use to solve these. That is not the only method. Let me show you a different way you can solve these that you might appreciate, or that might ruin your life and make you rue the day you signed up for college algebra. Okay, so I'm going to call this like, it's going to be method number 2. Now, remember what we did a little while ago with lowest common denominators. Let's focus on that for just a second. I want you to look at the denominator of the top fraction and the denominator of the bottom fraction and tell me what is the lowest common denominator of those two. X plus 4, x minus 4. That's the lowest common denominator, right? Okay, here's what we're going to do. I am going to multiply this and this by whatever it takes to give me this lowest common denominator, okay? Here's what I mean. I'm going to multiply the top by x plus 4, x minus 4. And I'm going to multiply the bottom by x plus 4, x minus 4. I'm going to multiply both by the lowest common denominator. Okay, how is that going to help me? Well, let's see what this looks like after I do that. So on the top here, I will have 8x, x plus 4, x minus 4 over x minus 4. That's just this piece, right? And on the bottom, I will have 3 x plus 4, x minus 4 over x plus 4. Now I'm going to really exaggerate the fraction line in between them so you can clearly see which one's the top and which one's the bottom. You have a really exaggerated fraction line there. Because after you get that written out, after we do the multiplication, I want you to focus just on the top. Is there anything I can cancel on the top? The x minus 4s. Here's an x minus 4, here's an x minus 4, gone. Now look at the bottom. Is there anything I can cancel on the bottom? Again, I've got some stuff, x plus 4s in this case. All right. What am I left with in this top fraction? 8x, x plus 4. What am I left with in the bottom? 3x minus 4. And there's the answer. So a second method of solving the same type of problem is to multiply both sides by top and bottom by the lowest common denominator. Now I hope what you're thinking is you're looking at this method and you're comparing it to the one that we did just a few minutes ago, the exact same problem. And hopefully what you're thinking to yourself is, this seems way easier than this. We got the same answer, right? Same answer both times. But this method, multiplying top and bottom by lowest common denominator, this method seems like it was way more work than this method. At least that's my impression. And if that's your impression, that's fine. Just use this method. They both work, obviously, you get the same answer. But where I think I'm going to manage to convince you that the lowest common denominator has its uses is in the other kind of problem, where you have like multiple fractions. I think I'm going to be able to convince you lowest common denominator is the way to go here, rather than adding the fractions together. We'll see. We'll see if I can convince you. Again, looking at this entire fraction and this entire fraction, what is the lowest common denominator of all four of these? A squared, A, B squared, and B. So obviously my factors are A and B, right? But what's the most that I have? What's the most A's I have? A squared, right? And what's the most B's I have in all four of them? B squared. So that's the lowest common denominator. So I'm going to multiply the top by A squared, B squared. And I'm going to multiply the bottom by A squared, B squared. Okay. Now when I multiply the top by A squared, B squared, both of these get multiplied by it. So this is going to be B multiplied by, I'm going to go ahead and do separate colors so you can see the new part. A squared, B squared over A squared plus, and 1 times A squared, B squared is just A squared, B squared over A. On the bottom, I've got A multiplied by A squared, B squared over B squared plus 1 times A squared, B squared is A squared, B squared over B. I'll give you just a minute to catch up there. I have my doubts that this right here has convinced you of anything other than the universe is out to ruin your life. But some magic is about to happen in this problem, because look at all the stuff that can cancel. A squared's gone. A squared and A can cancel. I have 2 A's up here and 1 A down here, so this 1 A cancels with one of these A's, so instead of A squared I have just A. On the bottom, B squared and B squared canceled. And here, this B cancels with one of these B's, so this one's gone, and instead of B squared I have just B. So what am I left with? B times B squared is B cubed plus AB squared. And on the bottom, A times A squared is A cubed plus A squared B. And that's the way, I like it. Not a fan of that one? Well, the two methods that I just gave you are interchangeable. If you really like the first method, you're like, I'd prefer to just add those fractions together and flip and multiply, totally fine. If you prefer the lowest common denominator method, that's totally fine too. You come up with the same answer either way, so you pick your favorite and you use that one. As long as your favorite is not copy the person who's sitting next to me, I don't care which method you use. Okay, last thing we're doing. Not forever, just till next week. I would like to take just a moment to discuss with you negative exponents. I know what you're thinking. Wahoo. Me too, guys. Me too.
Wahoo.
There you go.
Could we do social media?
We're not going to work this problem all the way through. I just want to show you how to set it up. Now, we have been talking a lot about complex fractions, and now it looks like I've given you a problem that is not a complex fraction. Now, this is gross, no doubt about it, but it's not a fraction that is made up of fractions, right? It's just one fraction. But a rule about negative exponents that you may have forgotten from the last semester is that when you have something with a negative exponent, you can rewrite it as a positive exponent by putting it under 1. What I mean by that is x to the negative first power is equivalent to 1 over x. Plus, now you do have to be careful because the only things that move down into the denominator like this are things with negative exponents. So if you look right here, 2 and x don't have negative exponents. They stay in the numerator. But the y has a negative exponent. It comes down into the denominator. What do you suppose this looks like? 1 over x squared minus 1 over x squared, and also the y to the negative first is down there with the x squared. So this problem isn't done. Now I need to use one of those two methods to simplify that complex fraction. We're not going to actually do that, because I feel like I'm going to have a mutiny on my hands if we do another one of those. But that's how you handle negative exponents. Let's do one more negative exponent problem. And then we will have sweet release. The most challenging part of these is keeping in mind that only the things with negative exponents move. So the 3x to the negative first, see these parentheses right here? That tells me the whole thing is to the negative first power. So all of the 3x moves into the denominator. Minus 2 is just minus 2. That's not a negative exponent or a fraction or anything. What about this? Only the x. So the 5 is in the numerator, and the x moves into the denominator, plus 2. And again, this one's not done. We would need to use one of our two methods we learned to simplify this complex fraction. But in the name of mercy, we will stop doing complex fractions, and I will assume that you get the idea. Does anybody have any questions about simplifying complex fractions?